Well, it's my great pleasure to introduce Olguta Buse from IUPUI. She's going to tell us about isotopy and homotopic stability chambers and blow-up ruled symplectic surfaces.
All right, thank you so much for inviting me. So like I said, I'm newbie to the Zoom talks. I do hope to see people in person in a conference sometime soon. But it's great to actually connect with the symplectic crowd in some way, even remotely. So what I'm going to talk about is work in progress with Jun Li. And so I apologize if some of you have seen some of this work that is old, that's included in here that I had to explain, so I don't get too obscure about what's going on. So this is about the symplectomorphism group. So this is an old story, of course, you all know. And so I'm going to very quickly go over the main problems. They are old problems. So we're going to be looking at basically topological changes through deformations in the symplectomorphism group. So we're going to change cohomology classes. Generally, there isn't a whole lot that can be done about that. It's actually very hard to even establish a language to move between one symplectomorphism group and another. The problems that have been somewhat settled were four-dimensional, and they start classically with the Gromov's results on CP2 cross CP2 and CP4. And then, CP2 and CP1 cross CP1. And then Dusa and Auroux did look at the rational rule surfaces. Sylvia Anjos and myself and Lalonde and Pinsonneau have looked at several types of homotopy descriptions of those symplectomorphism groups. A lot of the initial work that has been done relates in one way or another to the toric structures on those symplectic manifolds. What we really want to look at here is basically what type of symplectic deformation can we take so that the symplectomorphism group doesn't change, and can we see some discreteness in the symplectic deformations in the cone where the symplectomorphism groups change. So what we're going to try to imply today after the discussion is that if we look at the non-minimal rule surfaces, the cones are larger, and there is an actually interesting combinatorial structure or simplicial structure really in the cone. So there is a partition of the symplectic cone, which is driven by J-holomorphic curves. So I'm going to make that a little more concrete during the talk, where the exceptional curves play a special role, and they basically give us what we call stability chambers. And that will talk a little bit about the, then I will talk a little bit about the isotopy problem that's going to be inferred from this discussion. So we're just going to start with a few notations. We're going to be looking at the blow up of rule surfaces, and we're going to be starting our basis description from the trivial product here. So those are the notations for the classes, and we're going to be looking at the symplectic cone, which is well described by work of Lalonde, McDuff, and Li Liu later on. So that's also one of the reasons that you're more successful in discussing the changes in symplectomorphism groups in these manifolds, because the symplectic cones are well understood. This is an old story. The symplectic manifold is always described pretty much fully by the ratio between the base and the fiber. And in the more than one point blow up, we're going to basically identify the symplectic forms with a multi-vector. So those coordinates are going to be the areas of the curves that we exhibited before. we're going to normalize these forms. And so basically we take reduced vectors, and that's enough by work of various authors, but Liu mainly. So we're basically arranging in increasing order, in decreasing order, the areas of the exceptional curves, and the area of the fiber is stably 1. And we're not going to be looking at the non-trivial product, but the description in the minimal case for the symplectomorphism group in the non-trivial product has been done probably in Auroux's work or McDuff's work. And by what we said above, we're not actually missing anything by starting with the trivial product when we do more blowups. So this is again a result that's been used quite a bit to look at the extremal sides of the symplectic cone. We are basically just looking pairing positively with exceptional classes, and Liu say that that's basically the full description of the cone. So we're going to be referring to this pairing to exceptional classes as the exterior walls of the chambers. So we're going to propose some chambers in this symplectic cone. And the proposal is so that we actually expect to keep the symplectomorphism groups, homotopically speaking, stable within those partitions. So those are the exterior walls. So to actually introduce interior walls or partitions, so those are going to be n-1 dimensional simplices, which on their side are going to have their own simplices. So there is an actual recurrence in the way we choose these walls. What we're going to do is basically we're going to look at what we call non-regular curves. So this number we associate is the dimension of the co-kernel for embedded curves in those classes. And we're going to actually, for shortness, I'm going to be referring them as section classes. They're not quite exactly sections, but basically they're negative curves or curves with positive codimension, which are based off of a section class. So we're going to partition our cones with these hyperplanes that are pairing of the symplectic form with these negative classes. So of course, this is an old story. So here is the symplectic cone, the normalized one, for the minimal surface. So all the curves that we're talking about that give interior walls, which are just points right now, are the B minus KFs. And this is the old story that McDuff and Auroux exhibited. So basically that's where the symplectomorphism groups have changed. We have recently looked at the 1-point blowup. So the normalized cone is 2-dimensional. So what we see here is basically the symplectic cone. I should mention that, of course, the 2 horizontal lines, the top and bottom, should be dotted. So they are basically not included, those walls, since that's where you reduce to a minimal case. So the top line is, well, the bottom line is just a picture of the cone that you see above, the minimal model, and the top line in our picture is the non-trivial minimal model. And the partitions that we have in here are made by this section type classes. So we have studied this, basically this simplicial partitioning of the cone in the 1-point blowup, and we're going to present some results that say that basically, and I'll explain what basically means, symplectomorphism groups do not change as you vary the symplectic forms within those chambers. Here is a picture of the normalized cone for the 2-point blowup. So in the 2-point blowup, the normalized cone is 2-dimensional. Those arrows indicate the 3 planes that are slanted. Basically, one of them is so the three planes that are slanted, that are cutting through the interior walls, are given by section type curves, and we are proposing these chamber partitions. And there is a line at the top here, and this particular line at the top, it's marked every half integer, and that's actually a special line about which we can say a little more. And the picture in more multi-point blow up would get a little more complicated. So the triangles that we see here would be basically n-1 dimensional simplicial subspaces, which would have their own subspaces based off the fewer number of blowups. And the higher we go on, the more conjectural that split is. So what I am showing here is a partition about which we can actually prove some results on the first homotopic groups. Are there any questions so far? Okay, so let me just use some notation for the symplectomorphism group. So I am basically going to introduce here the symplectomorphism group. And I'm really only going to take its identity component. So we're really interested in the symplectomorphisms that are smoothly isotopic to the identity. And based off the results that we have seen so far, we would like to conjecture that if the norm of that vector is sufficiently large, which basically boils down in the size of the base being sufficiently large, then this symplectomorphism group has constant homotopy type throughout the chambers of the symplectic cone. One could basically conjecture that there are discrete chambers of the symplectic cone in the ruled surfaces. So, of course, I think a very interesting question would be, in general, at least for a four-dimensional manifold, is there some sort of similar expectation or hope for a discreteness such that you don't change symplectomorphism groups except at discrete changes, or let's say at least codimension 1 walls. So I don't know if anything is known even in the pi 0, maybe so I don't know if Mohammed knows that. So pi 0 has been studied, right? Are there any other examples of four-dimensional manifolds where you could say that pi 0 changes only through discrete changes? I
don't know.
No, okay. So so basically, it's very unclear if this conjecture has any hope to. Okay, Denis has a question. Is the area constraint or the external wall for B minus E the -1 section of the non-trivial bundle expected to hold in the case? I am going to talk about the Smirnov-Shevchishin case. So G = 1 is slightly different in terms of what we can say about the results. However, what I do want to say is this, because we have thought about the Smirnov-Shevchishin results, so I'm going to actually bring it up a little later. I think that these conjectural walls should hold better as the size is larger. And from what we've been understanding, the Smirnov-Shevchishin result is actually a pi 0 result in one of the lower chambers. So maybe I should be a little more precise what I mean by norm sufficiently large. So let me go one slide back. And here, for instance, this is the case where you're talking about genus 1. I believe, so we are actually saying that we don't know what to do about the first 2G minus 1 chambers. In other words, we cannot prove stability because the curves are more complicated there. So we expect that their example, so when you take G to B1 is the first chamber, basically. We expect that their example is lying exactly within that first chamber where we are not quite able to establish the stability. So they are basically picking off a fragile element in one of the chambers which are not regular enough because the curves are more complicated. Interestingly, they get to that result in a very different manner through some algebraic families in the space of almost complex structures. So it's very hard to actually identify it well in this model, but I don't know if that answered your question. Sorry, go ahead.
No, that makes sense. I thought they were even claiming that the picture of the symplectic cone itself is wrong because there's something to the left of the leftmost chamber. Isn't that what they claim?
I don't quite understand everything they claim, but what I can say is that their element doesn't seem to have a chance to survive in the homotopy limit, about which I didn't talk, but you know about.
That I agree, definitely.
So whether they say, so I do agree that morally the cone is more difficult to understand to the left. So in some sense, there is a chance that what they're saying is correct, but it's kind of hard to investigate with the curves at hand. So what we're doing now is basically we drop the leftmost parts of the chambers today.
Okay, that makes sense. Thank you. Sorry for derailing your train of thought.
No, that's okay. That's fine. We're gonna look at the right sides which are regular enough today. And we're acknowledging that things do happen to the left in a finite number of chambers. So I think that's basically where this stands. So yeah, let me go back. So in other words, there is a first chamber here where I think that their results happen, and we're not going to pay attention to that. Well, we would like to pay attention to that, but the curves are too difficult. All right, so that basically it's taking care of this part of the sentence which says norm is sufficiently large. So their case falls in the other part of this. However, I do believe that there is discreteness even in the left side of the chamber in this symplectomorphism group. So I don't think there is a continuous ripple change in the pi zero. So I think that their elements should live for some discrete amount of time, but they have not fully identified that. Okay, so let me go back to some more of the old stuff to explain why are we basing our homotopy conjecture, what are we basing it on? So McDuff in 2000 with some sort of contribution from me in 2011 showed that minimal one line that I pointed before, which is the cone of the minimal case, is constant on the chambers. So basically the conjecture is true. Even in the minimal case, I should point out that the analysis does not work well for the higher genus case. So you need the case to be more than 1. So that basically leaves away all those questions on the left that we're encountering. It also explains that basically the walls come with a codimension number, so you could flag them if you want, and the groups that have the homotopic groups that have an index below that flag or below that codimensions don't change. So you can actually say there may be changes in general. In the minimal cases, the changes are actually well recorded. There is a more recent paper of 4 authors, Anjos, Lili, and Pinsonneau, which say that if you look at the general multi-blowup case in the rational case, there are chambers within which you do not change the homotopy type. They don't have, so the chambers are descriptive. There isn't a whole dig into the combinatorics of the chamber in the paper, but the changes are basically based off the negative curves that we're proposing. So what we're proposing now is to look at the non-rational cases that are left up. We have more success in the 1-point blow-up. So basically in the 1-point blow-up, the homotopy type does not change in the chambers. Again, we're throwing away the chambers on the left because the analysis can't be tackled correctly. And so the one here refers to a blow-up. So this is true for all chambers. And we have recently tried to mimic everything we have done in the 1-point blow-up for the multi-blow-up. And there are some, I'm going to explain a little bit later where on the curves we're stuck that we're basically unable to establish the full stability in the chambers, but we can actually establish stability in the pi 0 and pi 1 groups. So the chambers that we proposed are good enough to show some partial stability. Not only that, but I don't know if you looked at the top of my 2-point blow-up picture, there was a line which I said it has half sizes marked. So that is the equal size 1/2 blow-up line. And that line actually has a decent enough analysis to basically establish a result that's very similar to the McDuff result on the minimal line, except that it's more frequent. So there are different type of curves coming in there. So conjecturally, all the homotopic groups are the same within chambers high enough in the cone. And the changes may or do occur in this codimension. So the wall is labeled by a curve A, which has a codimension. And conjecturally, all the homotopic groups with index less than that codimension -1 don't change as we cross that wall. So one could actually enhance the changes into the cone. Here is an easy picture to remember for the 1-point blow-up. So here we're a little more careful to say what we leave in and what we put out. So those are the 2 type of chambers that mimic the length 1 intervals that we saw in the minimal case and their corresponding curves. And you may see in red here several numbers. I apologize, my picture didn't work out quite as well, but those are basically the codimension numbers that label each one of those chambers. So you basically could just combinatorially extract which symplectomorphism groups do not change as you cross which one of these chambers. Now, I'm just going to go a little quicker over this because I feel that maybe everybody has seen this many times, the methods. So the methods are basically enhancing somewhat older methods that Dusa used in 2000 and been used several times since. Let me know if you're not familiar with this, but I feel that everybody has seen this many times. So there is a vibration that Kronheimer proposed maybe back in the 90s. And that's basically saying that if you take the space of symplectic forms isotopic to a given class and act on it with the diffeomorphism groups, then the stabilizer of that is this symplectomorphism group that we're looking at. And Dusa basically decided that she would like to study this within the context of deforming the symplectic forms. And what she proposed is to replace the space of symplectic forms with the space of almost complex structures. There are many good reasons to do so, but one good reason is that you could move directly between the spaces of almost complex structures by inclusions if you're lucky. And that's basically her homotopy vibration. And we're going to be considering that vibration. I think today, actually, we are not looking at the tamed ones, but at the compatible ones for some technical reason, but they are also making this vibration work. So what I'm going to say is that I'm going to be quickly switching from trying to understand symplectomorphisms to trying to understand groupings of spaces of almost complex structures in relation to a given symplectic form. And this is the reason that basically you go through this vibration and they translate into results on symplectomorphism groups. So from now on, we're just kind of ignoring the symplectomorphism groups until we're ready to state a result. So we're trying to understand this space of almost complex structures. That symplectic vibration is true in general. However, there isn't a whole lot that one can say about that large space of almost complex structure in a general context. However, if you look at, let's say, very ample four-dimensional manifolds, aka ruled surfaces, there are lots of curves to play with, and they play a very good role there. They basically help you stratify the spaces for a fixed U and enhance them with a good topology. And that's what Dusa proposed back then. And that's something that would, for instance, work very poorly, or rather not work, in, let's say, a K3 surface or an elliptic surface, which has a few Gromov invariants. So so it's a very interesting question. What is the space of symplectomorphism group for such manifolds, which are four-dimensional, let's say a K3 surface, where you don't have that many curves to show richness of the space of almost complex structures? And so I've been thinking about that, but there isn't a whole lot of insight on how to get to that beyond maybe pi0 results, because these methods don't really lead to a whole lot. Well, okay, but in the case of ruled surfaces, everything falls nicely into place. So this is a pretty convoluted definition, but let me try to explain what's happening. I am taking curves that represent certain homology classes, embedded curves. So I'm going to take that collection of homology classes, and I'm mostly interested in those classes for which the codimension number is positive. So in the old world, it used to be called negative self-intersection curves. Right now, because of the genus, there is a little bit of discrepancy. We're going to take the subset of J's, which could have all sorts of positive curves, but the only type of negative curves that they admit are the ones given by this collection C. And really, in our cases, the collection C are mostly one homology type. So I'm not really going to present any collections of more than one homology. So you could think of that C as being those section type B minus KF minus EIs. So it's just a one homology class. And then the results fall into place. You have basically codimensions for these objects, and then you have a top stratum, which of course you have to pay attention to and plays an important role. Here is the McDuff stratification. She basically identified the only negative curves, and she said that the strata that give that come with positive codimensions are the ones identified by these section classes, and then there is the top strata that you have to drag along. Oops, excuse me. In the 1 point blow up, we have been able to give a similar stratification. So we have a new type of strata. So remember that between two integers, you had two lines, and that's basically associated with the curves B minus J, F minus E. So I'd like to say a little bit more about what's going on in the many point blow up. So there is a stratification. There are many non-regular curves. So by non-regular, I mean curves with codimension that is positive. The exceptional curves that we actually need to keep track of, though, are not the best behaved. So I'm going to try to point out what's happening there. When we're basically going to make this ad hoc splitting here. So I haven't explained how we move between different strata, between different spaces. I remove the U. but our goal is to move the strata along with the U in an organized manner. So what we're doing here is basically we're establishing two types of codimension 2 strata. One are the regular ones. So there is a table here indicating what we're saying. The B plus KF minus sigma EI, so that's the middle column, which comes exactly in codimension 2. And the other one comes with codimension count from an exceptional curve that's broken in a very specific way or degenerated. So basically it has to have those type of components, and it should have no other negative curves because that would automatically put it in a higher codimension strata. So of course, this ad hoc splitting is not going to be enough for us to understand a full stability result. But if one is interested in pi 0 and pi 1, if you can move these three types of strata along with U, then that's enough to establish the constantaneity or the stability of the first two homotopic groups. So I'll just say very few words about the inflation package because I believe that everybody has heard about this. So basically, in any 4-dimensional manifold, and I'm actually going to stick to the B plus equals 1 because of certain compatibility improvement. If you're given an embedded holomorphic curve, you could move the cohomology class of the symplectic form in the direction of the Poincaré dual of that curve. If that curve is a positive self-intersection, then you could move it as far as you want. So that's basically giving you a direction in the tame symplectic cone. So that's going to be still taming the original J, and that's important for us. And if the curve has negative self-intersection, then of course, for the taming purposes, you need to stop somewhere where the curve still is positively a positive area. So we can actually extend this for broken nodal curves, this taming inflation version, which does make the work slightly easier, but it's not fully essential for what we want to say. And in order to actually move the strata, we need to identify some curves. So let me just give you an ad hoc package from results that Zhang produced. I think it's maybe more than one paper, but I'm just going to say it's the 2018 paper. So he is specifically looking at the non-rational ruled surfaces. And then out of his results, here is what we can get out and use. For each fiber class, we can find a unique fiber class passing through every point. So that basically means that we have a singular foliation with the basis sigma G for every J. So I should really make that important, that that foliation is J-holomorphic foliation for the given J. So it's not for some J, but for any J, we can foliate our manifold with F fibers. However, some of them are singular. We do have exceptional holomorphic curves, but they may or may not be embedded. They can have rational reducible components, which sadly may have singularities, or at least that's not something that we can eliminate right now. And lastly, we have enough embedded curves in the classes that we were interested in, which is somewhat quick consequence of Gromov invariance, as long as they basically have positive area. So that's just going to basically say there are no issues for us to identify the section type curves to inflate along. And so we're going to basically proceed and use some inflation. Here is what McDuff did for the minimal case. So remember that line broken at integers is the chamber. So you cannot just, well, you can, but you don't want to just move the whole space at once. But what you want to do is basically move the strata so that you can keep track which strata pops in as you pass to a new chamber. So her stratas are simply labeled by these curves. And so the spaces should be equal if you can show double inclusion. The open space, so the methods are the following. To move up, basically increase the size of the base of mu is easy because you inflate, you use the foliation and increase on Fs. And that's going to be true for all cases. To go down, the situation across chambers, so to go back from mu at infinity down to the most accessible chamber that you can go to, you're using the negative curves. In the case of finite codimension strata, because they are basically defined based on those, and you are using embedded positive curves if you happen to be on the top strata. So we're going to try to mimic something similar in the case of the 1-point blow-up. So remember, moving up, very important is there is a foliation. In the McDuff case, well, Zanks gives us a foliation that's pretty well behaved in the 1-point blow-up. So I'm just going to summarize this as there are several moves that one has to make so that we show that the space of almost complex structures behave well. Moving up towards mu equals infinity uses the foliation. So that should not be an issue. And by moving up means you inflate along the F. Moving down, well, it does happen to take into account what strata you're into. So if it's a negative strata, you're moving down on the curve that defines it. If it's on a positive strata, then we use those Zhang's results to move down on the section type curves that we have. The more interesting thing to pay attention to is how do you move within a chamber? So how do you show that once you've reached the optimal chamber, the space of almost complex structures don't change? So that within the chamber inflation is maybe a little bit awkwardly done in here, but there is a good takeaway. It uses Fs. So it uses classes F and exceptional classes. So I'm going to show that again in the higher case. However, the exceptional classes are not very useful if they are not embedded. And that's not a problem here because the exceptional classes are embedded. So you can actually inflate towards the walls of the chambers and establish the full stability. But when we try to do something very similar, in the case of the many points blowups, we no longer can guarantee exceptional classes that are embedded. So for all type of strata, we have an issue showing that you could move towards the walls of the chambers without changing the space of almost complex structures. That is the main reason we basically stay away from the top strata and we only establish the pi 0 and pi 1 results. And that's a little bit of, so one has to pay a little bit of attention, but if you're not doing a very bad degeneration of the strata, you can still inflate. However, in general, one doesn't have a full understanding on how the exceptional curves degenerate. Conjecturally, if you could show that you don't have bad singularities, let me rephrase. If you could show that all the components of the degenerations are maybe multi-cover, but their images are embedded, then one could actually have some success to show full stability. But we have not found a way to eliminate bad singularities in the components of the exceptional curves in general. So we're basically going to put all those higher codimension strata in the third bit. And what we're going to do there is basically say, well, we can move around the codimension 2 strata and the open strata, which has embedded exceptionals. and establish the partial conjecture for pi 0 and pi 1. There is one case where the exceptional curves don't break too bad, and that is the half line in the top. I call it the half line, so that's the equal size blowups in the top of the 2-point blow-up picture, which of course exists in general for the multi-point blow-up. So it's a single line, and for simple homological reasons, you don't break the exceptional curves too badly there. So you can actually write some sort of theorem which is very similar to the minimal case, except that it changes each half interval. So that means that you establish the full homotopy conjecture there. So let me talk a little bit about what Denis was asking in the beginning. So there is this concept of topological limit. So these upwards inclusions are not too terrible to establish. They use the foliations, and they happen in all cases. So that's enough to actually draw a line through the chamber towards infinity. Let's just say a horizontal line, otherwise you have to do a little bit of shenanigans there. But in general, any other lines could be handled. For simplicity, keep in mind the half line, for instance, and look at the homotopy limit, the topological limit in this one-way inclusions. So you can call that limit G infinity. And that's something that McDuff did study, and she came up with something pretty nice in that limit. She came up with a smooth model. So basically, here is what happens. The A infinity, the limit of all the spaces that are included, is just the union of the AUs or A mu's. She observed that that space is homotopy equivalent to the space of foliations of a product. So that's the minimal case of sigma G cross S2. So you're actually going to replace studying the A infinity, which leads to studying the G infinity, as we explained from the Kronheimer sittings, with studying the space of foliations. And you can act on this space of foliations with the diffeomorphism groups. And the stabilizer is actually a very nice group. So it's called the group of fiber-wise diffeomorphisms. So it's essentially diffeomorphisms that preserve the base in the fibration. So they are described neatly in this base diagram. So these fiber-wise diffeomorphism groups, which are essentially going to be homotopically the limits of symplectomorphism groups, are connected. They are nicely understood in this minimal case. So she has more results about them than just connectivity, but I'm not going to mention them here. Well, since the spaces A mu are actually not changing in the lower codimension, that basically says that you remember the pi zeros of the symplectomorphism groups. So on short, the symplectomorphism groups are connected for mu large enough because of this at the limit infinity argument. We basically mimic the same description. You have to pay a little bit of attention to what you replace the fiber-wise diffeomorphisms. There isn't an actual fibration there, right? So we just have to explain what do we mean by a liftoff in a blow-up. So it's a smooth model still. That model doesn't work well in general for the multi-point blow-ups because we cannot control what type of singularities are in the fibers of the foliations. There is one case where we could do it, and that's the half size case. And so basically we propose similar models in the two cases that we have here, including the genus 1, which is the torus that I was asked about. So we do have the models in these two cases. However, these models behave a little differently. So you still have this foliation. Nevertheless, with the exception of the genus 1, one can lift a then twist from the two-dimensional picture below and obtain a non-trivial pi0 element in this group. So that's different than the minimal case. So that basically implies that since this comes as limits of symplectomorphism groups, the symplectomorphism groups are disconnected for large use in these settings. So here is the interest in this. So you're looking at the isotopy problem. You look for exotic symplectomorphisms. There are several examples of those. So I'm just going to restrict to the rule surfaces. When she wrote the paper, Dusa conjectured that for any minimal rule surface, I'm not sure she wrote minimal, but I think the expectation was minimal. Any symplectomorphism that is smoothly isotopic to identity is also, sorry, the other way around. There is an equivalence between smooth isotopy and symplectic isotopy. And it's almost established in the minimal case by the results that we said before. By almost, I mean that, remember that we're not quite able to look at the lower bit. So we need mu greater than G. Let me put it this way. There may be a little better improvement there, but there is a small portion of this ratio that is just not covered. So one could still look for some counterexample in the minimal cases, although the belief is that probably there are no counterexample in the minimal cases. So Shevchishin and Smirnov in 2017 didn't look at the minimal case, but they did look at the torus case. And they came up with some very nice example of, so in the 1 point blow up of the genus 1 case, they came up with a very nice example, non-constructive example, but nevertheless, it's an example of an exotic symplectomorphism. So like I said before, so this is basically the question that Denis asked, that example takes place in the lower chambers. It does not survive actually, so one could prove that it does not survive in the homotopy limit on the genus 1 case. However, the question is still interesting because in the genus 1 case, we cannot say one way or another. We cannot say whether there are robust pi0 elements in that case. So their description of the elliptic diffeomorphism is not geometrically constructive. And we cannot say in the genus 1 case if there is an element. So it's basically unclear if, like Denis said, torus is an outlier in these pictures, or if one could expect the pi0 to still mimic the other cases, but the topology of the limit, it's not good enough for us. Oops, excuse me. So in any case, one would like to understand a nice geometric description of the elements that we claim that are there, providing symplectic elements that are exotic for the higher genus. So let me just actually finish up by basically trying to say where I believe this situation is. I think that it's not necessarily true in non-minimal rule surfaces. So in all rule surfaces, I believe there is a recurrent simplicial chamber partition, which is basically not drawn in my pictures because it's still too poor to show the recursivity for the 2-point blow up, but that this is driven by all the J-holomorphic curves with positive codimensions. And not necessarily, like the second point would say, not necessarily the section type curves. So I believe that for the higher blow-ups, like 3 or more, there are other type of negative curves that may give partitions identifying higher homotopic groups that aren't shown in the picture so far. And basically one can enhance the what dimension jumps in this conjectures. We decided not to do so. But the more interesting thing would be to basically pick on the word may be changing. So just because a group can change, it doesn't mean that it does so. And it's actually fairly difficult to identify non-trivial higher homotopic groups elements. So McDuff had them identified, and they are actually nicely related to the algebra of the classifying space of the symplectomorphism group. So there is this concept of Samuelson products or Whitehead products in the classifying space. And based on some work I have done long time ago on the minimal case, I believe that one could actually identify non-trivial higher homotopic groups from the study of the equivariant actions in the cone in general. And fairly recently, maybe 4 years ago, Tara Holm and Liat Kessler came up with a very nice algorithmic description of how do you identify the non-equivalent, or at least how you count the non-equivalent S1 actions in all these blowups. So if one could understand that very carefully and pick up all the fixed points curves for these actions, I think that those would be the maybe only candidates for the changes in higher homotopic groups, again, for mu large enough. So maybe I should just stop here. I prefer not to go into more details here because that would basically take a lot of setting up. So I think I maybe will just stop here. Thank you.
Thank you very much. Any questions?
So I have a very stupid question, which is not quite about your talk, but about what comes before. And I think on slide 3 or something, you had a description of a symplectic cone. And anyway, I think there was a statement there that the size of the blowups had to be less than mu.
I'm going somewhere there. Hold on.
Yeah. I
mean, I could have mistakes.
Just before that.
I mean, your stupid question is
here.
mistake in my slide, yes?
So there's a statement here that E1 has to be less than mu.
Yes. So, well, I'm not giving you the full cone.
Oh, so this is not the whole symplectic cone?
No.
Why not? Or what? I mean,
basically, we would like to take enough of the cone so that we describe all the possible scenarios. So, for instance, even in the minimal case, I'm just giving you like a crappy answer. So, for S2 cross S2, the cone starts at 0, right?
No, I understand that you normalize things, so it's up to scaling. That makes sense. But
well, let me see. So why is U1 less than mu? All of them are less than 1.
Yes, that I understand. But if mu is smaller than 1, if the sigma g is smaller than the S2, I believe that.
I don't think we want it. I mean, I'm not sure. I mean,
well, I mean, it's not a case of interest to you because you look at the large mu limit. But right. I think my understanding of what Shevchishin and Smirnov do is it relies crucially on doing a blowup that's bigger than the size of a sigma g. The fact that, in fact, the size of a blowup can be bigger than the size of a sigma g factor.
Yes. So, see, the thing is, so we have been actually thinking about this. So there are several papers written about symplectomorphism groups. And they all look at those interesting cases, right? So that's for the smaller sizes. So you are absolutely right. So in the case of S2 cross S2, it's not very interesting because you just flip, right? But when you reverse the order of the blow up, like you say, I think we don't quite understand very well what happens.
No,
so
but so I'm not talking about symplectomorphisms or anything complicated. It's much more basic than that. The question is, what is the symplectic cone? Is the symplectic cone of these things actually understood? Because I think the left boundary in these diagrams is not actually a boundary.
No, it's not. No, there is like almost a parabola in there. No, so my cone is not accurate on the left, and there is like I don't know if I'm showing myself. So there is like almost like a parabola type thing that gives a boundary there. So in this side here, sorry, how do I annotate? So, okay, so the answer is I don't think it's fully understood. You are right. So
I think it would be good to kind of state that clearly, because in all these talks until now, I had never realized that in fact people say, oh, this is the cone of classes that admit symplectic forms, and actually it's not, because there's weird constructions that push you outside of the world of symplectic forms that we can actually visualize and understand.
So I remember thinking with Jun about the 1-point blow up, and there is like a whole like an enveloping line of curves there, and it can be quite complicated how that part looks in like beyond that first triangle, right?
Yeah.
Yes, there is a beyond that first triangle. So I mean, Jun, you're welcome to chime in, but I remember that there is like a round push out, and it's not round, it's like little segments that come out. So there is something going on there that we have not shown because we could not say anything anyway. And even in the first chamber that we do show, there are lots of changes that one could basically think about. It's like a Sierpinski's triangle type thing, right? Which we're not showing.
Oh, crazy.
Right, so that there could be basically as many changes in that small part that would mimic, you know, what happens in S2 cross S2. Like in S2 cross S2, if you look at the 0-1 part, right? So.
Oh, I see what you're saying. Yes, I see that for S2 times S2, 1 over mu has the same behavior as mu.
Yes.
That's a good reason to, that's a good way to think about that.
But then you have like that, how does that make the cone look like? It's gonna have like this accumulating little segments, right? By the 1 over mu. Of course, that's boring, so nobody's gonna bother to talk about that, right? But in this case, if I were to draw something very nice for you in there, it would be complicated. And I'm not sure if Sierpinski triangle is maybe the best word to say. But basically, there is this projective geometry. You go from very big to very small type thing.
Yeah.
So you could squeeze in lots of little triangles there. So you could easily probably make a nice combinatorial 1 hour talk about what happens in that part. And yes, you're right, and they are right. There is like a push off of that line. So that first line of slope 1 is not accurate.
However, it is a boundary, but it's an internal wall, not an external one or something.
I agree. Absolutely right. That is correct.
Thanks.
Yes.
Okay.
And there is like little lines that go like this. Yes.
Okay. Now I'm happy. Thanks.
Right, but basically, you know, we choose the lazy way out. We're like not looking at that. We're trying to see what happens regularly, like where the curves are as decent to us as possible, right?
Sure. So I understand this is completely opposite to the whole point of your talk.
It's the large scale limit talk.
Yeah.
Yes, that's what we're trying to say. Yeah.
Can I say something?
Yes.
Yes. Hi, Olguta. In terms of the symplectic cone.
Martin. Yes.
Yes. In terms of symplectic cone, I think that the description given by Li and Liu back in 2002 still hold. So the external walls are always given by being, you know, classes being positive on exceptional classes.
Right. But so, that doesn't mean that.
So in terms of purely symplectic cone, we have a description, but the finer stratification, of course, gets complicated in this region.
Right, but what Denis was saying is correct. The B minus E is not part of the symplectic cone wall, right? There are other things there for like other size of blowups. Like when we normalize, we throw away a bunch of things that would appear in the lead description that would give some stuff.
Yes,
there.
of course, exactly. Yeah.
That's what. So I think Denis was bugged by what we preserve when we normalize. I think.
Mhm. Yeah.
From the higher cone. So I don't think anybody was claiming that their description is wrong. It's just what do we do when we normalize? We kind of not pay attention to what's at the left, right?
Yeah.
Okay. Yeah, thanks. And hi.
Right.
So yeah. So here there is more. Right. Okay.
Any other questions for the speaker? So can you say, so you mentioned in sort of the last slide that like you need to know something more about negative curves, or more curves would be needed in order to understand the sort of chambers for low U. Could you say a little bit more about that? Like what is it you would need? Is it like there's some questions about existence?
Yeah, maybe I should ask you about it. Right. So here is what happens. I'm gonna go to the compendium of curves we picked from. Basically, you know, we thought about Gromov invariants and then we just found them all that we could anyway in Zhang's paper. I'm trying to get there. And so maybe I should just speak. All right, so here, I need more than this. So the question is how much more, right? I would like to understand what's the deal with those exceptional holomorphic curves. So remember that we're not talking generic J's because they are useless for symplectomorphism groups, right? We're talking any J. So unfortunately, the generic holomorphic curves that are embedded for generic J's do break down, right? So we're very interested in how they break down. And there is some partial description on how they break down for the general case by Zhang. And there are ways to get around the bad degeneration or bad breakdown in several cases that I've mentioned. But in general, I think we cannot eliminate the possibility that one such holomorphic exceptional curve breaks down into many components, very negative, where the each irreducible bit is not only multiply covered, but with a very bad singularity. So multiply covered, we could probably handle because we take the underlying geometric curve and it's embedded. So here is the thing, we need embedded or at least nice for inflation. So what's embedded or nice? So we can handle embedded or we can handle nodal so that we can inflate. But if you're thinking of a random breaking of a curve E, I don't think we can inflate on that. So do you have any inkling on how can you look at the limits of holomorphic curves and get rid of bad singularity components, like say they aren't there in one setting or another? That would be very helpful. So that's basically the main thing that would be exceptionally useful.
I see. So first of all, it's not really a question about just like Gromov with invariance, because you really you need these sort of non-generic J where you're seeing these.
Definitely. In the whole slide, I should have pointed out, there is no use for us to understand curves for just generic J. Of course, that's the game. We understand the curves for generic J, but we have to really understand how they break in general so that we can identify embedded components for any J. Otherwise, we cannot do the game, right?
I see. And so for the simple, so if I understand correctly, like you take this take like a curve with a cusp, with a simple cusp, for example. So like the worst thing after a nodal curve, like, so is it just, it's not clear if you can inflate along such things? Or...
No, right. I mean, I don't know how to inflate on that. Right. We need to have like a unified way to say those cusps cannot happen, whether they, I mean, of course you could say, well, they happen, and that means that all those pi's, higher pi's are going to randomly change around, but I fully believe that's not true. I believe that the higher pi's are going to be changing at very nice discrete walls, you know? But how to move things within the chamber, that, so yeah, we don't want cusps. You could have cusps in other curves. So we're like really stacked down on the exceptional curves, the generations. Does that make sense?
Mm-hmm. Yeah, thank you.
Yeah. Like all degeneration, not like we can't use results like there is a good degeneration. We have to basically say all degenerations are this nice. Yeah. So I mean, on the other slide, the last slide, I also said that I could milk some more the negative curves by using the equivariance to actually identify higher order groups, but that's different. And that's something we're probably going to do, at least in some setting. So there is more to be said based off the same curves, but you have to understand the equivariant blowups and very constructively. And that's a whole different setting. And that could be difficult. You need to compute some Gromov invariants, but it's maybe doable. But what the degenerations of the exceptional curves look like, I am not sure. That's, yeah.
Okay, so maybe let's thank Oleg again, and then if anyone wants to ask any more informal questions, feel free to stick around. So yeah, so thanks again for a very nice talk.
And thank you for inviting me.